Hello everyone, I am Mathieu Vavrille, and today I will show you my work with Truchet and Charles Prud'Homme during my PhD about solution sampling with random table constraints. So what is solution sampling? Solution sampling is the task of returning a solution of a constraint satisfaction problem randomly and uniformly. It is notably useful to have a user feedback. For example, you will have non-deterministic solutions. Also useful to have equity because you won't have any solving bias induced by the search strategy of the solver. And also to have coverage of the solution, which is a close task to the diversification of solutions, which is the task of having representative solutions. So my contribution here is an algorithm to sample solutions, which is inspired by the thesis work of Kuldeep Singh Mill, by adding table constraints and by using a CP solver as a black box. So black box here means that as long as your CP solver implements the table constraints, you will be able to use my approach. Experimentally, I implemented it in Java using the constraint solver Choco solver, and I show that there is an improvement of the randomness compared to random var-dom, and also that the running time remains in the same order of magnitude, which is great because we have more properties of randomness. First, I need to show you how to generate random table constraints. You have to choose two parameters, which are the number of variables that you will have in your table and the probability to keep a tuple. So in this example, you just enumerate all the tuples for these 4 variables, and you pick each tuple with probability 1/2 in this example. So you will keep all the green tuples, and all the red tuples will be removed from the solutions by propagation. These tables ensure that when adding a randomly generated table with probability p, then on average, you will reduce the number of solutions of your problem by a factor p. We want to reduce the number of solutions because a perfect strategy of sampling would be to enumerate all the solutions and then to return one of them randomly and uniformly. But in practice, it's not possible if you have plenty of solutions. So you have to reduce the number of solutions by using, in my approach, table constraints to be able to enumerate a small number of solutions. Now my sampling algorithm relies on this principle. So we choose a pivot value, kappa, and we use function find solution, which will enumerate at most kappa solutions. And here kappa, you have to choose it small enough to not to spend too much time finding all the solutions of your problem if your problem is big. So this function gives the property that if it returns less than kappa solutions, it means that it returned all the solutions. Otherwise, it means that there is more than kappa solutions and we have to reduce the solution space. I will be using this figure to represent the search space where the triangles are all the solutions of my problem. So here is my algorithm. I will show you step by step. I take an example with kappa equals 4. So first we just find kappa solutions just to be sure that if my problem is not satisfiable, then there is no point in trying to sample a solution in a problem with no solutions. Then I add a random table which reduces the solution space. I find kappa solutions, at most kappa solutions. Here I see that it returns 4 solutions, which means that in the whole model there is still more than 4 solutions. We have to keep on going. I generate a new random table. I enumerate at most 4 solutions. We still have 4 solutions, which means that there is more than 4 solutions in the problem. We generate a new random table constraint, and then we see that we have no longer any solution, so we just don't add this table to the problem. We remove it. We go back to the previous step. So we generate a new random table, which will on average not be the same. We enumerate at most kappa solutions, and here we see that we have 3 solutions, which is strictly less than 4, which means that it returned all the remaining solutions, and then we can just return a random element from this set. So now, my implementation. I implemented my approach in Java using the solver Choco Solver, and I applied it on 4 different problems. So first, the encore roasting problem is a planification problem. The feature models and the Renaud-Megan configuration problems are configuration problems. And there is the N-Queens problem, which is a toy problem that most of you probably know. So how to evaluate the approach? We evaluate it experimentally. So we evaluate the impact of the parameters and versus the random-random strategy, and we evaluate on the quality of randomness and on the running time. The results show that my approach has a better randomness than random-random, the random strategy, but there is still no uniformity guarantee, and that there is a reasonable running time for my approach. So now, just the theoretical definition of random-random is a search strategy during the search of the solver, which will randomly choose a variable x that is not already instantiated, a value small x in its domain, and will make the decision x equals small x. So this random strategy is very easy to implement, but is not uniform, and that is what we will see on the next slide. So here I plotted the p-value depending on the number of samples I did. So the p-value is a quantitative value showing the distance to the uniform distribution. It's a measure of uniformity. So we see, for example, for a same distance to the uniform distribution, with random-random, so the random strategy, we can do 100 samples, but with my approach, for example, with my approach using 5 variables in the tables, we are able to do more than 600 samples. So we see that as my approach goes to 0 much slower than random-random, it means that I have a better uniformity. So I'm closer to the uniform distribution than random-random. What we can also see on this graph is that as we increase the number of variables, you improve the randomness, because for 2 variables you can do 200 samples, and for the same distance to the uniform you can do 600 samples with 5 variables in the tables. So here it was on the feature models problem with kappa equals 2 and p equals 1/2. So it shows that increasing the number of variables improves the randomness. Now in terms of running time, you have here the time of random-random in the second column, the time of table sampling in the previous to last column, and I gave the ratio between the two here, and so in green it's when my approach is faster than random-random, and we see that on some problems we are up to 3 times faster, and on the other problem we see that we are at most 7 times slower, which remains in the same order of magnitude. So I can give you the impact of the parameters, which are well explained in the article. So if you increase the number of variables, you will improve the randomness, but it will have a cost in terms of running time. If you increase the pivot kappa, it will improve the randomness and have no impact on the running time. So, or at least the impact is not clear. If you increase the probability, it has no impact on the quality of the randomness, but it has a negative impact on the running time. So you can choose a small probability, which will improve the running time. To conclude, I give you a sampling algorithm, which can use a solver as a black box, so you can use your favorite solver and implement it. I show that it's an improvement compared to random-random in terms of quality of randomness, and it's in the same order of magnitude in terms of running time. And there is many ideas for the future, for example, to use other constraints and have a specific application to optimization problems, and analyze the structure of the problem could be a great idea to have a better uniformity. Thank you for your attention, and if you're attending this live, I can answer any question now. Thank you.